Okay, so welcome everybody. This is the final review meeting of an InnovateUK funded project called Model-Based Design and Quality Planning. And I am Gianmaria Bullegas from Perpetual Labs. So I'm going to do a brief round of introduction to give everybody a little bit of context. This was a project funded under the Made Smarter call promoted by BASE and InnovateUK. It was a collaborative project that was led by Perpetual Labs. Perpetual Labs is a startup based in London that specializes in model-based engineering solutions and tools. And is a collaboration between, as part of the consortium, we also have the University of Lincoln, led by Professor Minisagi, Professor Malecki, and Professor Chiappetta, and LPW Technology, which is part of a group called Carpenters Engineering, which specializes in additive manufacturing technologies, and Autodesk Research UK. The project was also supported indirectly from some industrial advisor. We have from Boeing, Airbus, BAE Systems, and I'm going to do a little bit. So we actually have some guests that are interested now. Okay, sorry. We actually have some industrial guests here. We have Michael Christian and Lucas Giranic from Boeing US and UK, respectively. We have Antonio Prizzavento from Airbus Defence and Space UK. We should have Rebecca Arista and Nicolas Gay. I apologize already in advance if I'm murdering everybody's name. I haven't seen them, but they should be joining. And we should have Chris Forrest from BAE. Chris, give me a shout if you are here.
I'm here, John. Hello.
Awesome. Cool. So that's a full board. And then we have some guests. Federico Mele from Studio Management LSC. We have Nicola Bates from Horizon X Ventures. Edward Kozasic from the Creators Fund, and Mark Felsk from Remus Capital. Okay, just a brief reminder, this was a 6-month project that was extended by a month due to some delays at the beginning due to recruiting problems. It is essentially a feasibility study to demonstrate the fundamental ideas around the technology. So, what are we trying to demonstrate? I'm going to try to give you an introduction to the general challenge that we're trying, the broad challenge that we're trying to tackle in this feasibility study. So this is a quote from a recent report from the European Space Agency, which says that the challenge in the development of complex engineering systems is to implement digital continuity between data stored in different information artifacts. Now, what does this mean? If we consider a complex system like an airplane, it evolves from just an idea, that light bulb, to a simple sketch, to a full engineering design, to the real thing. So that drawing is meant to be happening on the diagonal of a three-dimensional space. So we have the evolution from idea to the final product that happens in a three-dimensional space that it can be declined along 3 axes: domains and disciplines, the life cycle of the product, and the supply chain. So let's have a little bit more of an in-depth look at each of these axes. So if we look at domains and disciplines, what's happening is that the information artifacts, so information artifact is just a fancy term for any kind of document or files that contain data. A CAD file, a simulation file, a report. So all of these is produced by different domains and disciplines. Hardware design, software design, systems engineering, project management. The problem at the moment is that all these different information artifacts don't really speak the same language. There are links, meaningful links between them. Like a CAD file can contain the geometry of a part, the data, and can, for example, can contain the geometry of a fixing hole and even the tolerances. But the reason why those tolerances have been fixed because of a fitting with another part, or because of a limitation of a manufacturing process, that kind of implicit knowledge and the links between the other artifacts that use that knowledge, that is usually just in the heads of the engineers and in documents that are written in natural language. These links are very, very difficult to capture in an automated way. The second dimension is the product lifecycle. We can imagine that the design of a complex system evolves through time and in multiple iterations, from like simple requirements definition to a geometry to a simulation. And throughout the product lifecycle, multiple versions of each of these artifacts are created by different teams, by different companies. How do we keep track of what was the right version used in a certain context? How do we have traceability across domain, across the supply chain? How do we do version control in this very, very heterogeneous ecosystem? The third dimension is the supply chain. So what's happening is that even if we have like the cutting edge model-based approach, usually what's happening is that different companies own different levels, different hierarchical levels of the system. An OEM will own the top level, the system level, and then it would pass down the requirements to the tier 1, which own the subsystem and the components level, and then flows down to the manufacturer. Now, the problem is that all the models that are produced at the different level of hierarchy are strongly decoupled. What this means is that we need to make assumptions at the beginning of the modeling effort that by the time that the requirement has flowed down to the bottom might be completely outdated, because the process is completely waterfall and there is no feedback loop. This results in a process that is very rigid. We might end up with a lot of integration problems towards the end of the design cycle, and those are usually the very, very, very costly ones. And ultimately, we end up with a suboptimal design, because even if we end up not having integration problem, we have probably designed something that is not optimal. Okay, so the challenge, we have rephrased it slightly. This challenge is to implement digital continuity, is to capture the links between the data contained in information artifacts in the 3 dimensions of across the discipline, throughout the life cycle, and along the supply chain. Okay, so the objectives of this project are to tackle this problem. We want to capture the links between data generated by different domains. We want to enable version control and traceability throughout the product lifecycle. And we want to connect different modeling paradigms across the different levels of the supply chain. Okay, so quite ambitious, quite broad. Let's see, what's our vision for this? Ultimately, what we want to build is a search engine for engineering data. Imagine an automated system that you ask a question in natural language. The system spans through an ocean of information artifacts, an ocean of data, and doesn't just give you the raw data, it actually gives an answer. It understands your question and it gives an answer. Does it sound familiar? Probably because that's how modern search engine works. So today, if you ask Google for Tesla Roadster specs, Google doesn't just give you a link to a website. It actually understands the context of your question and gives you an answer, gives you the answer that you're looking for. But how does it do that? How does it understand that we're talking about Tesla the car and not Tesla the inventor or Tesla the unit of measure? So it turns out that the way that a search engine does that is through a knowledge graph. A knowledge graph is a data structure that allows you to capture not just the data, but also the links between the data that give it, and enables a machine to understand the meaning and the context of a human question. It turns out that knowledge graphs are actually part of a much broader set of technologies, which are called semantic web. Now, the semantic web is quite complex, it has multiple layers, but ultimately you need to remember 2 concepts. What's an ontology? An ontology is essentially the technical term for a knowledge graph that enables automated reasoning. It enables a machine to infer implicit knowledge from explicit. And I'm going to explain what that means in a few minutes. The other thing that you need to remember is the web ontology language. This is essentially the de facto standard language that is used nowadays to capture ontologies. The large majority of available ontologies are developed now. Okay, so if we come back to our original challenge about digital continuity, and we keep in mind what we just learned about semantic technologies, we can reframe this as the fundamental question that we were trying to answer in this project is it possible to use model-based engineering techniques and semantic web technology, so knowledge engineering, to achieve digital continuity? This is the fundamental objective, the fundamental question that we are answering in this feasibility study. And the next section is about the case study, because, sorry. Essentially, we didn't want to do just an academic exercise. We wanted to produce tools that actually solve realistic problems. So we needed a realistic problem to apply these technologies to. There is a strong lack of data out there because we are in a field where companies are very protective of their own data. And also we wanted somehow to control the entire span of the data from the top level system model to the last design of the last school. So what happened, we decided to create our own data set to do a simulated supply chain exercise, where we are designing a complex aerospace system, including the perspective of the system from the perspective of the OEM, component of the system from the perspective of a tier 1 supplier, and then the manufacturing that is associated with the component. In this case, we have selected as a system the environmental control system of an aircraft, which has as a component a heat exchanger. That heat exchanger is designed in detail by a tier 1 company, and then it's designed to be manufactured using additive manufacturing technologies. And now I'm going to introduce the people that actually did this simulated supply chain design. So Neil, if you want to take over from me. No, I think Joe takes over from me, right?
Yeah, thanks, Jan. So as Jan said, what we wanted to do was try and capture the key activities that take place across the supply chain. And so this starts with the OEM. One of the first activities requires the system architect to develop the high-level architecture of the environmental control system. Click ahead, please. One of the inputs into this activity will be a definition of the mission context. In this example, this is being presented as a pair of SysML diagrams captured using a tool like Magic Draw or perhaps Enterprise Architect. Our system of interest, the Environmental Control System, or ECS, has been highlighted here. That's it. Click ahead, please. Another input at this stage will be the system requirements. A selection of these requirements are shown here, and they include functional, performance, interface, and environmental requirements. Head, please. So the system architect will then begin to develop the functional architecture of the system, and a portion of this is shown in this SysML diagram. At this stage, we would like to include traceability between these functions and the relevant requirements. Head, please. From the functional architecture, we can begin to define the logical architecture of the ECS. So subsystems of the ECS have been defined in SysML in order to realize the required functionality. And interfaces between these subsystems have also been defined where necessary. Head, please. We can continue this process by further developing the passenger air conditioner in this example, or PAC, which has now been highlighted. Head, please. Components of the PAC subsystem are identified as the architecture is further developed. And at this stage, we have an architecture that we can use as the basis for a system simulation. And if you click ahead, please, I'll pass over to Andre, who can talk you through this.
Yes, thank you, Joe. So yeah, my role as a simulation engineer is to take the system architecture, system requirements, and scenario definitions to develop a simplified physics-based simulation model of the system for requirement verification. So here we took the system diagram and converted it into a open source physics-based Modelica model of the system. And all the major components are captured as they are, all the important ports also captured in the model. If you click Jan, please. And then we can use this model to obtain simulation results, which would help us to obtain and refine further component level requirements, which we can then pass on to further down in the supply chain. And at this point, I give it over to Neil.
Thanks, Andre. So now we've talked about the system level, we're going to move on to the component level, and specifically the design and additive manufacture of this heat exchanger. So much like the system, we're going to discuss sort of the current state industry and how that measures up to where we want to be in this future state that Jan's talking about. So next slide, please, Jan. So when we get to assembly or a component level, there's actually a standard method in place in automotive and now more like aerospace called Advanced Product Quality Planning, or APQP. And this has been developed to standardize aspects of product development process across the supply chain. And so it focuses on a number of key areas, including the design, process development, part, and the manufacture and the inspection of a product. And there's an expectation that additive manufacturing will need to be brought in line with this process in order to be fully onboarded with the likes of aerospace and automotive. So next slide, please, John. So if we actually take a look at the AM process chain, this is a sort of top level view. And at a glance, it doesn't necessarily seem that special, but we know from our expertise that there's marked differences in the process flow and lots of additional processes and data generation stages, certainly compared to maybe conventional manufacturing. So in order to understand how this and APQP would align, we needed to map out the AM process chain with APQP in mind. So next slide, please, Jan. And so this is where LPW and Autodesk really came in. So we were tasked with mapping out the full process chain for additive manufacturing from kind of component requirements all the way through to part certification. And at each stage, identifying all the inputs, outputs, and those key data artifacts that we've been talking about, including any of those APQP specific elements like FEMA. And so if you click next, this is actually what we generated. So hopefully what's pretty clear to you and that what became clear to us is this is a very, very complex system, particularly at the design stage. So actually the first 2/3 of this document from left to right is around the design, the CAD and the CAM side of things. And certainly the amount of data that was being generated, or the potential amount of data being generated, is going to be an order of magnitude maybe greater than conventional APQP is sort of set up to tackle. This is actually simplified as well, beyond a little bit simplified beyond maybe what we would see in some real cases. So next slide, Jan, please. This is just a bit of a zoom in so you can kind of see a little bit more detail. So those blue squares represent individual processes, like a simulation phase, a specific simulation, and then from those we then had these nodes where we detailed the responsible team, the inputs, the internal variables, those key outputs, and also what those output files may look like. And this is all necessary information for APQP. So if you go next, sorry. So yeah, now I'm going to hand over to Nick from Autodesk, who's going to just start off with a little bit more of a description of the work we did and the takeaways that we found during this case study.
Great. Can everybody hear me? Cool.
Yeah.
So yeah, in this program, I was responsible for performing design for additive manufacturing workflow on a heat exchange component using our own design and simulation products. So I'll keep this really brief. So Boeing has provided the consortium with requirements to design a heat exchange component. we managed to create a super cool design using Autodesk design tools. The main design feature was generating a gyroid-like core structure to maximize heat transfer while keeping the mass down. This internal structure works well for additive manufacturing because it doesn't require internal self-support and powder removal is manageable. Next slide. However, when using AM, this adds levels of simulation flexibility. These modern tools are required to try and meet the design and manufacturing requirements in the digital workspace. In this project, we managed to perform CEE simulation on the heat exchanger to accurately predict the flow regime on the heat transfer using Autodesk CFD. And we also performed CAM simulation to create the most optimal build setup and predict the build deformations and residual stresses using the Autodesk NetFab suite. Providing a rapid design can be challenging as a lot of processes and data generation are needed and then they have to be considered for design for additive manufacturing. This will ultimately drive up the simulation model management, increase manual feedback loops in the design process, and will significantly increase the simulation time, cost, and file sizes. To complete each workflow successfully, a lot of knowledge and data transfer has to be considered between teams, departments, and or new existing supply chain. Next slide, Jim. Here is an example of data exchange between two new supply chains. Ideally, a lot of upfront data is required to complete the CE and CAM workflows efficiently because the design is manufacturer dependent. For example, the designer needs to know the downskin and upskin surface roughness because this will influence the pressure minor losses and the flow regime, which is the key driver to meet the requirements that Boeing have set. Next slide, Jim. And finally, a design failure mode effects analysis was conducted for the heat exchanger example. What we observed is that when undertaking a DFAM approach, many requirements are needed and need to be considered. This can be time consuming and all levels of knowledge domain experts are required to complete this work successfully to identify the effects and outcomes of these failures and for actions. The spreadsheet belief just highlights just one requirement, which is maintaining the heat transfer power requirement. In reality, we expect to see probably 10 or more requirements. Next slide, yeah. So I guess my key take for this case study is undertaking design for additive manufacture on an advanced product requires a lot of complex processes and simulation requirements. To complete each task successfully, upfront data is required from OEM and the supply chain. And additive manufacture component will increase a lot of DFMEA requirements, which can be time consuming. So yeah, that is a wrap from me, and I'll pass it to Neil, where he will close the show.
Thanks, Nick. So much like Autodesk did for the design phase, what we needed to do for the production phase was actually run this example through as a paper exercise and generate the data and the artifacts, both to understand the full challenge on our side and also provide those template structures for the PL team to work with for the demonstrator. So next slide, please. So the first thing that struck us was when we looked at the outputs and data file structures was the number we had and the breadth that we had with respect to file type, etc. Next slide, please, Jan. And just to illustrate the range of data file structures we have, we can see some examples here. And a lot of these, you may notice as well, aren't necessarily in readable form. So we have things like the heat treatment curves, which is basically just an image from the supplier, the reports, PDF reports, they may be PDF, they're not often readable, and ranging from feedstock certificates through to base material properties. The second thing that we realised is that we didn't actually have any examples of some of these key PPAP elements because we're not necessarily in that industry yet. So things like the process flow and these really vital PFMA documents, we didn't have those. So we needed to carry out that exercise much like Autodesk did for the design phase. So next slide, please. So here we've got a snip from the process flow diagram. So this is a step-by-step breakdown of the additive manufacturing process. We've just taken the actual laser powder fusion process itself, and then the previous or secondary steps. And we've identified the key and critical steps. Now, this would largely be the same for any part, but what you can clearly see and what we discovered is that this is a very complex and data-heavy document, and it's also very heavy on manual entry. It's not easily automated as a process and as a file. So next, Jan. So that process flow diagram then is necessary because that feeds into the FUMA. And this is a really key document for a customer looking to ensure stability of their product and manufacture. And what's maybe not clear quite from the screen because of the resolution is that the snip I've got here represents just the first stage. So again, much like the Autodesk example, we have a very complex and detailed document. It's also noted that this, along with the process flow diagram, is a static data set. So what we mean by that is limited or pretty much no option for automation. And this actually applies really for a lot of the data artifacts that we identified throughout the mapping exercise. Okay, next. Okay. So then to summarise the activities and the learnings from the case study as a whole, if we consider the full process chain and the effort required in generating and managing the required data artifacts, and that this also then needs to be managed across the supply chain, not just within a company, we now see that there are a number of challenges within the current state of the industry, and these align really with what Jan's already identified earlier on. But these are the data exchange will be very challenging due to the variety of different formats, size data sets, and also the accessibility of the data. It would be very difficult because a lot of these are stored locally within different companies and different locations, or even within those companies and departments. The data itself, these artifacts can be very static, and there might be limited opportunities for automation and a lot of differences in formats, for example, so a lot of translation issues. So the first outcome of the case study was that it helped us really fully identify all the key bits of that data across the supply chain, and it allowed us to really appreciate the scale of the challenge, particularly for additive manufacturing. And in doing so, also validated what Jan introduced in those earlier slides. The second outcome was that we generated or got examples of all of those key data artifacts and outputs in the process mapping phase, and this was then allowed Jan and his team to use these for the CloudFS demonstrator. So now I'm going to hand back to Jan, who's going to move on to that and start talking about ontology development.
Hi, thanks a lot, Neil. So we move on into the ontology development and the knowledge graph. So just a refresher on our challenge: use model-based engineering and semantic web technology to achieve digital continuity. So where did we start? At the moment, there are a lot of ontologies available out there in the literature. So we started from a thorough literature review, and we examined over 12 available ontologies for systems engineering, design, simulation, and manufacturing. These are just like, it's not even a comprehensive list. What we found out is that all of these ontologies are developed in OWL, which is definitely the dominant language. They all have a fairly well-developed terminology side of the ontology, but at the same time, they all lack a well-developed what is called a box, the assertional box. So essentially, they are lacking the connection with the actual data. And they all are missing an actual modeling methodology associated with the ontology. And ultimately, these led to the fact that these are all academic exercises. None of these is actually used in an industrial environment. So we started asking ourselves, okay, why are these being developed? These ontologies are being developed in academia, but not really picked up by the industry. So we came up with three main culprits of the reason. Two are essentially technical. One has to do with OWL as a language. OWL is a very low-level language, very much like C or C++ compared to a Python or a Java. It's very, very time-consuming to model in OWL, and it's very easy. It's very error-prone, and for people that don't have, as a very steep learning for people that don't have a background in formal logic. The other problem is the very, very poor tool support, in particular regarding tools that allow graphical user to interact with ontologies through a graphical user interface. The third problem is less technical and more philosophical in a way. This is going to be, it's going to be familiar with people that have dealt with ontologies before, but a lot of those ontologies in the literature subscribe to a principle that is called realism. Realism essentially states that we start from the physical reality, the modeling from the physical reality. The problem with realism, a very well understood problem, is that it starts when you start to trying to incorporate data artifacts into ontologies that are based on this assumption. You start creating recursive loops. And this recursive loop can easily lead to inconsistent models. Okay, so these are our three key problems that we had that came out of this state-of-the-art review and that we had to solve. So how did we approach them? The first problem of OWL being a very low-level language, we solved it by building a higher level abstraction on top of OWL. We examined different meta models and different type systems, and we landed on something called TypeQL, which is a very intuitive property graph type system. And we implemented a TypeQL-inspired framework on top of OWL, and we built a compiler to translate TypeQL syntax into OWL. The second step, actually, I'm gonna explain briefly the TypeQL type system. So it's very simple. Everything in our universe of discourse can be categorized in entities, attributes, and relations. And relationship have attributes, have roles that connect entities with other entities. So this seems complicated, but if we have an example, it's really, really simple. We have two entities, a company called Tesla and a person called Jan. The two entities are connected by a relation, an employment relationship, which has two roles, an employer and an employee. Tesla plays the role of the employer, Jan plays the role of the employee in the employment relation. And Tesla has an attribute, which is the incorporation date, and Jan has an attribute, which is the date of birth. Okay. Now we can expand this with, for example, another relation. The company has the property of an AM machine, and build what is called, like expanding this to build what is called a property graph. The other cool thing about TypeQL is that reasoning is done via single type inference and conditional rules. This is different from typical reasoning in OWL, which is done by restrictions, which is much more, I want to say, complicated, not intuitive for non-logicians. Let's put it like that. Conditional rules are, in my opinion, a lot more intuitive. For example, in this context, we can state that an employee has access to all the resources of the company. And what happens is that the reasoner, which is a software that is able to analyze the knowledge graph and infer new knowledge, would infer a new relation between Jan, which is an employee of the company, and the machine, because the machine is property of the company, so Jan will have access to the machine. Okay, so that was the type system, the reasoning. The next step is build a new tool to support all of this, which enable collaborative multi-user experience and not manipulation and editing of the knowledge graph using graphical user interface, version control, querying, time travel, and a lot more. Okay, so now let's introduce the GraphSF platform. And I have a little video, hopefully it's gonna work. Can you see the video? Someone give me a shout.
We can see the screen.
Yes, we can.
Okay, so we're gonna start. First of all, we load up the platform. GraphSF developer, we log in with our credential, we are greeted with the collection of our projects. We can log in into a project, and then we can start to explore the project. The first thing that we want to do is interact with the ontology. So here we can explore the ontology using a graphical user interface. We can see the attributes, the entities, person, organization, tool, and the relations, employment, property, access. We can also add a new entity, like a charity, using the graphical user interface and save it. The other way that we can interact with the ontology is through a diagram tool. So again, we can explore the ontology and plot it and visualize it, actually see the property that each entity has, and for example, see the employment relates a person with an organization. The other way we can interact with it is a scripted way. So in this case, we can use TypeQL syntax that automatically gets translated into OWL. And you can see how much longer, how much terser the TypeQL is into syntax is compared to OWL. Okay, now we have the machine, then the new entity created, we can save and move on to the knowledge graph. In the knowledge graph environment, okay, we can see the history of the knowledge graph, the different commits, and see how the knowledge graph has changed through time. And we can query the knowledge graph. I'm gonna actually, I'm gonna stop it here for a second. The other really useful thing is that we can actually query the knowledge graph to focus on particular instances. So in this case, the organization, Tesla. And from one node, we can explore all the neighboring nodes. In this case, we can see that the neighboring nodes for the organization are Joe, which is an employer, and the AM machine, which is a property. Then we can explore, again, the connection for Joe, and it will show that we have a relation. The relation is highlighted in red because it's an infer relation that is automatically derived by the reasoner and added to the knowledge graph. Okay, so this was a very, very simple walkthrough the platform with what we have called a hello world example. So if we move back to our presentation, we have solved the technical, we have developed a solution for the technical issues that emerged from our literature review. We still have the issue around the realism challenge. So what we did there, we developed a completely different modeling approach, which we call a data-first approach, in which essentially information artifacts are first-class citizens in development of ontology. And this was really, in a way, revolutionary. We spent a lot of time trying to develop on the realism assumption, and we hit a lot of dead ends throughout the project, which probably have been the same dead ends that the ontologies in the literature that we have been examining hit, and that's why they haven't been really used in practice. Ultimately, when we decided to have the data as first-class citizen, everything became much more intuitive and started to make much more sense. And now I want to show you essentially what this looks like in the context of our case study. So I'm going to switch again to our demo, and this is the full demo. Again, we log into the project, we are greeted into the dashboard. I'm going to talk about the dashboard a little bit later, but we can go to the ontology. Again, we can explore our ontology. Again, in this case, you can see that the ontology is much, much more developed. And we can see all the different attributes and definition of the different blocks. So in this case, what we have done is we have developed a modular ontology, which includes support to model system architecture, to model a process flow diagram, to model the FMEA analysis, and to model analysis and verification requirements through simulation. Like before, you can explore it. You can explore the ontology through a visual interface that we call patterns, which is a much more intuitive way to understand how the ontology is supposed to work and how to model. Okay, and here we have again the editor. Once again, you can see how there's the TypeQL syntax is compared to the out version. Okay, and now we can save again and move on to the knowledge graph. And here you can see the full shebang, and all of it is under version control, so we can actually look at the evolution of our knowledge graph throughout the project, from when the system engineer submits the mission architecture, then the passenger air conditioner architecture, then when Nick and Neil submit the FMEA, the FMEA, and finally the whole shebang. Okay, now you probably say, okay, this is not much more less complicated actually than what Neil showed before. The key difference is that this is not static artifact, it's a dynamic one that we can organize. So one key way to organize is name graphs, which are essentially just subgraphs of the full thing that we can use to highlight specific aspects of the project or the system. We can collect the graph of the system architecture, or the graph of the production system. Okay, again, this perhaps is, you want more granularity, we can use our query language to query specific nodes. So we can start with the mission context. Okay, and then we can navigate by expanding from one node to its neighbors. So we can have all the different blocks that compose the mission context. We can expand the ECS further and see all the different blocks that compose the ECS and the interfaces. And we can see the blocks that compose the passenger air conditioner. And then we can even go and explore the interfaces and the connection between the interfaces. In this case, it's interesting to notice that between the ECS and the bleed air system, we have a connection because they exchange fluid, hot air. And because of this exchange of fluid, the system is inferring that there must be a connection between the two interfaces. Okay. 1 second. Okay. The next step is to, so we have seen the system architecture. Let's have a look at the process flow. Okay, so we start from now the mission context, the ECS production system. Okay, once again we can explore the hierarchy and see that the production system is made of multiple steps, and we can break them down. So we can break down the manufacturing of the heat exchanger in all its sub-steps, which are the steps of the manufacturing process. And yeah, I'll roll it back a sec. Okay, so here we have explored the entire hierarchy of the process flow, which is all the information that was contained in the process flow diagram and the PFMEA that Neil showed before. So the next step is to investigate the function and the failure mode and effects. We start from the top level function. We can investigate the hierarchy of functions. So functions are divided in sub-functions. And we can investigate the allocation of each function. I'm gonna find it back in a second. Yeah, you can see that function 1 is allocated to the ECS, which is a component of the architecture. So we are actually established a connection between the function allocation and the architecture of the system. And we can see that one of the sub-functions is actually assigned to the passenger air conditioning. But we can also explore the failure mode associated with that function. So the top level function has 3 failure modes: mission failure, excessive fuel consumption, and passenger discomfort. And then we can expand and investigate the causes of each of these failure modes. So in this case, we can see that the top level failure mode is actually dependent on a failure mode of a sub-function, which is associated with another component that is a subcomponent of the ECS. So what we have done here, we have connected the FMEA with the process flow diagram with the system architecture. And we can investigate, using this process and this system, we can investigate failure modes and the causes from the top level mission failure down to the malfunctioning of one single element of a manufacturing machine. And all of this is collaborative, so you can have multi-user collaborative experience in the platform. It's under version control, so we can monitor the evolution of the system, of the graph throughout time, and have traceability of what happened and what decisions were taken at each stage of the design, and is automatable through automated reasoning. And just one more thing on the version control, another pretty cool thing that we can do, I'm kind of gonna roll it back, is that then in the dashboard, for example, we can show how certain typical budgets that we want to track during an engineering process, such as the mass budget, the power budget, the cost budget, can be tracked across time, across the evolution of the project in each single commit, and easily plotted with a simple query and showed in the dashboard of the project. Okay, so this was our the demo of the case study in the GraphSF platform. Unfortunately, I had to do the recording because, as you can imagine, there is still some tidying up of the graphics that needs to happen there. But I think that we have successfully. I'm going to move back to the presentation. So that was the demo. I think we have, if we look back at our objectives, so the first objective was capture links between the data, so the meaning, and enable version control and traceability. I think that despite the fact that it's still in the prototype version, with the GraphSF platform, we have definitely checked these two boxes. And now let's move to the third part, which is about connecting different modeling paradigms. And now I'm going to introduce Andrei and Lorenzo.
Yes, thank you, Jan. Could you move to the next slide, please? So yeah, back at the sort of simulation side of things, we end up with two separate models implemented by different teams using different tools. The models are one at the component level, which is the CFD model of the heat exchanger, and again the system level model implemented in Modelica. So if you want to replace, let's say, the primary heat exchanger in the system shown on the left-hand side with the CFD model, we run into several issues. So we can couple them together by assuming some simplifying assumptions, which would yield suboptimal results. But if we don't want to do the simplifying assumptions, we can just brute force and connect them two together. However, that is very, very slow, because obtaining a single CFD solution would take at least 3 hours on a dedicated workstation, but during a Modelica simulation, we'd have to obtain those CFD solutions hundreds of thousands of times. So we propose a solution, and we've implemented it and tested. So if you move on to the next slide, please. What we do is we take the CFD model and apply a machine learning algorithm to it to obtain an intelligent approximation of the CFD, the heat exchanger, and we call that a surrogate model. And then we connect it to our system model through the common interfaces, and we insert it into our primary heat exchanger block on the left over there. And if you click once, please. This solution allows us to significantly speed up the computational time. So in the graph, we run the simulation over 1,000 seconds, and even with the surrogate embedded into the system model, the simulation took only about 30 minutes of real time. As a result, we can perform the evaluations of the design space much faster, and we can obtain an optimal design solution even quicker. This hybridization is seamless, and it's captured in the ontology, so that the knowledge graph is also aware of this coupling between the two separate models. And so yeah, next slide. And through this coupling, we achieve the third objective, which we set out to achieve in this study. So yeah, back to you, Jan.
Awesome. Thanks a lot, Andrei. So it seems like we have found a way to achieve digital continuity in the 3 dimensions, to tackle all the challenges that we set for ourselves at the beginning of the project. So we have a technology. Now the next step is actually anyone interested in this? And oh no, sorry. There is I'm gonna give you a little peek in what comes next for the platform, and then we're gonna actually move to the market study. So we gave you a little sneak peek into the platform, but actually there is a lot more in the works, in the background, that is not. It's quite far ahead, but it's not quite ready for prime time yet. And this includes, I would say, native support for all the different type of engineering information artifacts, including CAD simulation and manipulation, visualization of simulation results, like for example Modelica. And this is really interesting, using machine learning to recognize particular type of features in CAD design. And ultimately what I think is going to enable that Google-like experience is integrating the queries with natural language processing. And this is just a little preview of the integration of CAD visualization, the visualization of the manipulation of results from simulations, and the integration with different types of data set like CSV files and automatic importing of CSV and CSML into the platform. And and the next step is going to be the NLP. So this is what we have in the pipeline at the moment. As I was saying before, the next step is to ascertain if anyone is actually interested in this and if there is a commercialization potential. And for this, I'm going to pass down to Sefer.
Yeah, thanks, Jen. Can we move to the next slide, please? So I want to start the market research with emphasizing on the fact that how important knowledge management is within the industry in general. In fact, it is one of the main challenges of the next industrial movement, known as Industry 5.0. Big organizations such as IOF, Commons, JPO already identified this challenge and are working on various approaches to standardize data for the purpose of knowledge management. Next slide, please. So now, market study, we focused on the specific case of quality management to achieve zero defects production. We had 3 constructs for our study, and these were knowledge management issues, digital tooling to support quality planning and decision making, and some other challenges identified by the experts. We took a mixed approach in this study, and we had 2 phases. In phase 1, we employed a qualitative approach, and we interviewed domain experts. And in phase 2, we employed a quantitative approach and gave out a questionnaire to experts and stakeholders of the domain. Next slide, please. So we identified the existing challenges due to both technological attributes and specifically in the case of the aerospace supply chain. And these are the 15 challenges that you can see in this slide for the case of supply chain, for example. Next slide, please. We used the Likert scale with a range of 0 to 7, 0 being completely disagree and 7 being completely agree, to identify the most important challenges in the aerospace industry. And it's basically the important thing is that to note that inappropriate tooling has been the most significant challenge to achieving zero defects. So to summarize, can we go to the next slide, please, Jen? So to summarize the market study, the biggest challenge preventing net zero defects is inappropriate digital tools. And a key factor in designing such tools is an intuitive interface and user friendliness. And the most relevant factor to achieve commercial success is a subscription model with add-ons. And I hand back to John. Thank you.
Thanks a lot, Sepper. Okay, it's time to wrap it up, finally. So, to summarize the achievements of this feasibility study, we developed an open source dataset for a complex top-to-bottom engineering case study of our aerospace system. we developed ontologies for systems engineering, process design, and quality planning and simulation. We developed tools to support digital continuity across the supply chain, and we developed modeling patterns and graphical user interfaces to make these intuitive for the final user. We also developed a machine learning-based technology to achieve co-simulations and enable to connect different modeling paradigms across the supply chain. Ultimately, I think that we can safely say that this has been, in terms of a feasibility study, has been successful, and we have answered positively our initial question. We have demonstrated that we can use model-based engineering and semantic web technologies to achieve digital continuity. And we have also demonstrated that there is a market potential for this technology through our market study. Ultimately, I want to give you a bit of our vision for GraphSF and Perpetual Labs. Ultimately, our vision is the digital twin, which is a word that is thrown around a lot, is in practice, a lot of people think focus on the simulation and the data aspect. What is really missing to achieve a digital twin is capturing those links between the data, and we have called that the semantic twin. The semantic twin that captures the connection between the data and the co-simulation technology together make the digital twin. And the digital twin acts as the nexus between for the different aspects of the design for the different domains and disciplines. And ultimately, we see our platform GraphSF as being the nexus of collaboration between different market participants using these hosted digital twins on the platform. And ultimately, the vision is to develop a framework for what we call DevOps for cyber physical system, which enables design, manufacturing, and in-service support of complex cyber physical systems to be continuously integrated and continuously deployed. And with that, I conclude the presentation. I apologize if I've kept you for an hour, and I am more than happy to take any question. I'm gonna stop presenting because I'd like to look at everybody's faces. Okie dokes. Are we still, how many people have we lost? Not too many. Okay. Is there any question?
That was a fantastic presentation, Gian. Thank you ever so much. It's excellent. I'll be honest, I didn't really understand throughout the last 7 months exactly how this would come together. You've shown extremely well what the issue is in detail and extremely well how you've tackled it. But I think you've done a great deal more than that, haven't you? You've opened up the issue, a very, very large scale issue across the whole of what we're trying to do across supply chain, and you've offered a solution. And I think that's possibly a hole and a problem that not everybody realised was there. And I think this whole new paradigm of, well, digital twins are great and we're all talking about it, but what we need is something new and something different, not only to show that there's an issue with it, but to offer up a solution within a 7-month project, I think is quite remarkable.
Thank you, appreciate it. Any comments from our industrial friends?
Yeah, this is Mike. My mind is completely blown just because I have so many ideas in my mind of what to do with this in the next future. You simply put a very complex thing together, which makes it wonderful for people that aren't in the business. Leaders that don't understand will understand. I mean, Industry 4.0 is one thing, Industry 5.0 is another. And the fact that you're integrating so many different elements together that don't have, you know, similarities really, and it's that part's exciting. I can't wait to see what's next.
Awesome, I appreciate it. Thanks, Mike.
I think similar from myself. So Chris Forrest, Innovation and Growth Lead at BA Systems, Electronic Systems. Followed this journey for many years now. You've always been able to capture the problem so succinctly, and just to see how far you've come now, and so many notes I've written down to follow up with. Very, very impressive. Yeah, I've got lots of stuff to do back at base to present this to key decision makers. And in an abridged version, we're still couple of years into adopting APQP. We're sort of looking at the future tools as part of our digital transformation projects, but we're quite early days. We're a bit scared of taking too many big steps at the moment. We're looking at quite basic tool chains at the moment, but yeah, what you've shown here is really going to form key parts of our roadmap, and lots more discussions to come. So yeah, great job, really impressive.
Thanks, Chris. Appreciate it.
Gian, Antonio here from Airbus Defense Space. So eventually I managed to see your GraphSF after so many talks about it. Yeah, very pleased to see it working and to see some all the friendly faces there. So good job, really interesting. I mean, it's definitely mapping into the digitization journey that many of our industries are undertaking at the moment. We have a quite big roadmap in Airbus Defense Space. Well, in fact, it's the Airbus group, and there's definitely some interesting potential synergies and point of contacts that we should develop further. As probably mentioned in the past, due to the size of the organizations, is going to be some ground to cover in terms of seeing where Perpetual Labs offering maps into our roadmap, but it definitely is something that I wish to bring forward with our digitization organization. So yeah, it would be really good actually to eventually invite you for maybe some presentations, because a lot of people are still kind of cautious about all these things, and they have all sorts of different ideas of what it could be. So yeah, maybe we can, in the short future, maybe organize something so that people can start appreciating the maturity as well. I mean, it seems quite mature already, this platform. So yes, well done, guys. Yeah.
Thank you, Antonio. Appreciate it. Thanks a lot. Okay, anyone has anything bad to say? Okay. I just want to thank everybody in the team for the really hard work that they have put in over the last 7 months. It's been definitely been a journey, but yeah, thanks everybody.
Yeah, no problem, Jan, and thank you. And I'd just like to say, it is really impressive. We from our side, obviously, we saw kind of one side of it, and we did the case study, we pulled up together, and we could appreciate to some extent kind of how that was going to fit in. But seeing the demonstration as well, and obviously the last weeks we have seen bits of it, but it's nice to see it all come together, and yeah, it was a pleasure working on the project. So when it's good to see when they're successful.
Thank you, Neil. Thank you. Okay, so I guess if there isn't any other comment, I guess without any further ado, we can...
I do have a comment. Sorry. I was trying to unmute me. So yeah, Rebecca from Airbus Commercial. So thank you for the presentation. Very interesting. So I agree with the rest of the comments, saying that it's impressive and it's real clear the problems that you addressed, and interesting to see where you are. I would have one question because it's interesting to see your platform and what you're proposing. So I see you you got a TypeQL inspired syntax, and from there you transform to OWL. But if so, we're dealing with this kind of problematics right now, and thinking of going out of that problematic and control the syntax that I want to apply. So what would you think of the openness in the next steps of your platform in this direction?
The openness.
To be able to define my own syntax to control what I will be modeling in from there.
Oh yeah, totally. I mean, at the end of the day, we did define our own syntax. We used we modified TypeQL, and we have a very flexible compiler. And ultimately, we see the platform as having multiple paradigms. One of the things that we're definitely going to implement next, I don't know how much are you up to date with the SysML2 development? So SysML2 is built on a metamodel called the kernel modeling language, KRML.
Yeah, correct.
So the next thing that we want to do is to implement a KRML framework on top of OWL so that we can natively translate SysML2 into the OWL framework to leverage the reasoning.
Okay, interesting. It will be interesting to see what you bring in there, because this is one of the things that we're exploring currently. And so thank you, and very impressive.
Thanks. Okay. Anyone else wants to raise their hands? Okay, it doesn't look like it. So I guess at this point I can safely let you go to your weekends, guys. And thank you so much, everybody, for attending and for paying attention for an hour and 15 to some pretty thick technical talks. And yeah, I hope that we're gonna follow up in the next few weeks and months with all the different connections. So thank you, everybody. Have a great weekend.